Hello, my chemists. Let's keep going with resonance with a new topic. We have really never broken things down into electron donating and withdrawing groups. I used this terminology back when we were doing SN1, SN2 reactions, but it wasn't the highlight. So let's really dig into what is an electron donating group and what is an electron withdrawing group. And first, of course, we never write out the whole thing. So EDG versus EWG. Now, exactly as the name says, an electron donating group actually pushes electron density into the system, where an electron withdrawing group pulls that density out from the system. But the key is, can you determine which species will do which one? Because that will affect the overall reactivity. All right, there's two conditions to be considered when determining whether an atom or a group of atoms is donating or withdrawing. Oh, look, induction and resonance are two friends from the past. So one of the big reasons we talked about this in the acid-base chapter is to get a feel for what induction and resonance is. And then we're going to use it now to talk about reactivity. All right, is there one that is more important than the other? Okay, in the jolly world, I have found that resonance tends to win out. That doesn't mean it's 100% of the time, but in a nice rule of thumb, resonance wins. So if in doubt, go with resonance. Okay, so we've got induction versus resonance. And right now you're thinking, I don't even remember what those words are. Did we really talk about those in the first semester? Why, yes. Yes, we did. All right, so let's start with induction. So induction is the pull that a system feels. From neighboring groups. Remember, it decreases the further away it gets. So it decreases with distance. So for instance, when we were doing the acid-base chapter, let's put a chlorine right there. So let's talk about this hydrogen right here. We had a chlorine, and if the only thing we were thinking of is induction, this chlorine will be slightly negative, which will be slightly positive, which will then make its neighbor line up, let me see, with a slightly positive, slightly negative. And remember, I'm trying to remove this one in the acid-base chapter, so I was trying to leave a negative right there. And do you see they lined up next to each other? So this is helping because the chlorine is pulling density away so that the negative is at least next to somebody who's partially positive. All right, so that's induction. When I say distance, let me see. So this one was 2 carbons away. So this one, so those are the 3. This one would have the most, if you will, feel. This one would be the second because it's further away. This one would be last. And there is a limit. Eventually, it doesn't even matter anymore. So induction is the pull or the effect that the system feels from the neighboring groups. And we're going to learn you can either do donating or withdrawing. And then, of course, resonance. Well, if you want to have resonance, you have to match all the conditions of resonance, and that doesn't matter about distance. So if I had resonance and I had a chlorine right here, well, you still get resonance no matter what. They wouldn't all be equal. Okay, they wouldn't all be equal, but you still get those resonance effects because you have a P system. You have a P system. So that's the difference between the resonance and the induction. And now we just have to decide who is doing what, or can they do both? Can they do both? All right. Electron withdrawing groups. This one I think is a little bit easier to wrap our minds around, so we'll do that one first. So electron withdrawing groups, they pull electron density away from the system. Density. All right, how are you going to do that? Well, normally it's electronegativity. But it could also be because of resonance. What, Jolly? That's induction and resonance. Yes, it is. So we're going to look at a carbonyl group. So let's just go back to our acid-base issue. So I'm wondering about the effect that that carbonyl has on this hydrogen. All right, well, what can happen? Because of induction or electronegativity, that side's going to be slightly negative. This one's going to be slightly positive. And remember, we're trying to, in acid-base chemistry, put a negative right there. So the inductive effect is working. Okay, it's beautiful. It's working. It's pulling away. But I also need to consider what is happening with the resonance. And with the resonance, it's not just a partial positive, it's actually a formal charge, true positive. So I would say this one's a little bit more important. But they are working together. So the induction and the resonance, which is all nice and lovely, but they don't always have to work together. So who has a dual nature? And again, this is a jolly term. But I want to look at the electron donating groups. They push electron density into the system. All right, so here's the funky one. I call it the dual nature. I am electronegative, but I have lone pairs that can be part of resonance. And the best example of this dual nature are the halogens. Okay, so let's take a look at this. And I'm just going to throw in a benzene because do I want to throw in a benzene? Sure. All right, I'm going to put a chlorine on this benzene. And my question is that chlorine pulling away? Is an electron withdrawing group, or are those lone pairs pushing in? Now, the answer is yes, chlorine is electronegative, so there is going to be some pulling away. So if I did a dipole arrow, it would look something like that. Okay, instincts are correct. But I also need you to look at what are all those lone pairs doing in a pi system, in a pi system. And in that case, watch this. If it pushes in towards it, it would push this one out. And I would have a resonance structure that looks like, let me see there. Oh, but guess what? Then this one could flow and should have left myself more room. Okay, that one is still there. And I just reformed this one, so the positive is there. Now, and then one more would take it back. Look at all those resonance structures. Okay, anything that has that many resonance structures is going to be pretty stable. Now, I do not like that that's a positive. Okay, so in each of these cases, the chlorine becomes positive, but it had electron pairs to push in. So even though it is electronegative, having those lone pairs is actually going to be more important effect. So generally, we do the reactions as if they are electron donating groups, as if they're electron donating groups. And yes, they are still electronegative. They have a dual nature. So what is the most important feature right now? And that is the fact that they can put electrons into that P system. Now that might seem counterintuitive. I promise it gets a little bit easier in time. All right. So if you look at all these examples I gave you, oxygen is electronegative, but it has a lone pair. Okay. The nitrogen is electronegative, but it has a lone pair. The halogens are electronegative, but they have lone pairs. So each of those have a little bit of a, fight going on. But these poor halogens really are having issues. But we would also say, the electrons pushing into a pi system is the most important. All right. This next question, number 8, is just playing with those electron withdrawing or those electron donating groups. And in your reference sheet, there is a little spot that tells you which is which. But right now, anything that is attached to a carbonyl, look out for those because carbonyls are electron withdrawing groups. Anything with lone pairs technically win for electron donating groups. All right. And then I give you a whole bunch of variations. And then just a review about benzene, because it's one of the best, visuals I can give you for this kind of system of pushing in and pulling out. So the group, if it is substituted, okay, so this is monosubstituted, the two that are exactly adjacent to it, those are called the ortho positions. Okay, 1, 2, 3, and 4. So ortho is called 1, 2, or ortho, or you can even shorten it to the O. Meta is 1, 3, and para is 1, 4. There's 2 meta positions, there's 2 ortho positions, but there is only 1 para position. And here is the little blurb I was telling you about that is on your reference sheet. Now, if you'll notice, this is a combination of a couple things. So strongly activating, moderately activating, that doesn't necessarily mean donating or withdrawing, but this will help us get a feel for it. All right, so in a reaction called electrophilic aromatic substitution, benzene will actually act as the nucleophile, and electron and withdrawing groups will change their reactivity for that reaction to occur. So remember, benzene is going to be the nucleophile, and nucleophiles have density to give. All right, I need this to be a nucleophile. So I need, okay, those pi bonds, I need it to go out and attack somebody. So the question is, do I want to put an electron donating group on it? Or should I put an electron withdrawing group on it? All right, well, what are we trying to do? We want benzene to actually be the donator, to be the nucleophile, so the electron donating groups would actually make it more reactive because it would donate some density, where the electron withdrawing groups would make it less reactive. So let's take a look. Let's put a electron withdrawing group. So if I'm just going to do a resonance structure, I won't do all of them. But if you'll notice, it pulled it away. The benzene is supposed to be the nucleophile, and what charge is on it? A positive. Okay, well, that's a terrible nucleophile. So an electron withdrawing group made it we'll just say, a worse nucleophile. So it's less reactive. Well, let's put a donator on it. Ooh, let's put an OH this time. Oh, it's pushing in. Woohoo! Look what's on the benzene now. It is a negative. Hey, it is a better nucleophile. And that's kind of the idea behind these electron withdrawing groups and the electron donating groups. All right, then a question, hey, can you tell me which one it is doing? And that is going to lead us to aromaticity, which is a completely different topic. So in a nutshell, can you now start looking at groups that are attached to what they're going to be doing? And generically, we're going to call it an electron withdrawing group or an electron donating group. And then we're going to go one step further and ask, what does that do to the overall reactivity? And then, of course, it depends on what kind of reactivity. But in that last example, I wanted it to be a nucleophile. So the donating group was more beneficial than the withdrawing group. All right. Until next time, jolly out.